Welcome! In this session, we'll explore an intriguing problem: check if an original string exists given two encoded strings. The problem challenges us to decode and compare two strings that combine letters and digits, making it a great exercise in string manipulation and algorithm design. Let's dive in and unravel the solution together. In this problem, we are given two encoded strings, S1 and S2, and our goal is to determine if there exists at least one original string that both S1 and S2 could expand into. An encoded string consists of letters and digits, where the digits specify how many times the subsequent substring of letters is repeated. For example, the string 3a, 2, bc, expands to a, with 3a, expanding to AAA and 2, bc, expanding to bc, bc. The task is to write a function that checks whether such an original string exists, given the encoded forms. The input consists of two well-formed strings that only include lowercase letters, digits, and square brackets. The output should be true if both strings can expand to the same original string, and false otherwise. Let's look at the first example. Here, S1 is 3a, 2, bc, and S2 is 3a, 2, bc. When we expand S1, the substring 3a gives us AAA, and 2, bc, gives us bc, bc, resulting in a. For S2, the substring 3, the 2, b, c, expands as follows: the 2, b, becomes ab, and repeating that 3 times gives a. Since both S1 and S2 expand to the same string, the output is true. This demonstrates that there is at least one original string, a, that both encoded strings can represent. Now, in the second example, S1 is 3, a2, bc, and S2 is 2, ab. Expanding S1, the substring A2, BC, gives ab, and repeating that 3 times results in ab. For S2, the substring 2, ab, expands to ab repeated twice, which is ab. Although these expansions look similar, they are not identical. The structure and repetitions differ. Therefore, since there is no single original string that both S1 and S2 can expand to, the output is false. Finally, in the third example, S1 is 10a, and S2 is 5a. Expanding S1, the substring 10a, gives us 10as, resulting in a. For S2, the substring 5a expands to aa repeated 5 times, which also results in a. Since both strings expand to the same original string, the output is true. The constraints for this problem ensure that the input strings are well formed, and they limit the lengths of S1 and S2 to at most 50 characters. Additionally, edge cases include strings without digits, strings with single or deeply nested repetitions, and strings with large numbers that still adhere to the encoding rules. This ensures that you handle a wide range of scenarios effectively. To solve this problem, we need to handle two encoded strings, S1 and S2. These strings contain both letters and digits, where the digits represent repeat counts for the subsequent letters. Our goal is to determine if there exists at least one original string such that decoding both S1 and S2 produces the same result. The challenge lies in efficiently managing all possible decoding combinations, especially as the presence of digits adds exponential growth to the number of possibilities. A brute force approach to solve this problem would involve expanding both strings fully, generating all possible decodings, and then comparing each pair of decoded strings. While this approach is conceptually straightforward, the exponential growth in combinations arising from the presence of digits makes it computationally infeasible for large inputs. Specifically, the time complexity is on the order of 2 to the power of m asterisk 2 to the power of n, where m and n are the lengths of S1 and S2. This makes it clear that a more optimized approach is necessary for longer strings. The brute force approach fails primarily because of its exponential growth in runtime and its heavy memory usage. Storing all possible decodings for both strings quickly becomes impractical as the strings grow longer. To address these challenges, we turn to more optimized strategies. The first optimized approach we consider is recursive backtracking with memoization. Instead of decoding both strings entirely, this method focuses on comparing substrings while recursively exploring the possible expansions of digits. By using memoization, we can avoid redundant work and significantly improve efficiency. Some key observations underpin this strategy. Digits in either string can contribute varying lengths to the decoded output, and we must maintain pointers for both S1 and S2 while tracking the current length difference between the parts being compared.
The base condition for our recursion is simple: if both pointers reach the end of their respective strings simultaneously, this indicates a match.
To speed up the process, we memorize results using a combination of the current indices in both strings and the current length difference, ensuring we don't reprocess the same subproblem.
The recursive backtracking approach can be broken down into a few key steps.
First, we parse the digits in both S1 and S2 to compute their repeat counts.
Next, we recursively explore all valid ways to match substrings by expanding digits dynamically during the comparison process.
If we find a valid match, we return true, otherwise, we return false. The time complexity of this approach is O, M*N*K, where K represents the range of possible length differences between the two strings. The space complexity is also O, M*N*K, due to the memoization table. This approach has several advantages.
By exploring only valid expansions rather than fully decoding both strings, we minimize unnecessary computation.
Additionally, memoization ensures that we do not revisit the same subproblem repeatedly, further improving efficiency.
We also consider an alternative optimized strategy, dynamic programming.
This approach shares the same intuition as the recursive backtracking method but uses a tabulation-based iteration to solve subproblems iteratively. By storing results in a DP table, we can avoid recursion depth issues while maintaining clarity. Dynamic programming leverages the same key observations as recursive backtracking. It iteratively solves subproblems using a DP table, which is structured as dp, I, j, length_diff. Here, I and j represent the indices in S1 and S2, while length_diff tracks the difference in lengths between the portions being compared. The process involves filling this table iteratively, considering all possible expansions of digits in both strings. The final result is determined by checking whether a valid match exists in the table. The time and space complexities of this approach are similar to the recursive method, at O, M*N*K.
However, dynamic programming offers certain advantages.
It eliminates recursion depth issues, making it more robust for extreme inputs. Additionally, the iterative structure of DP can be easier to debug, as the progression of the solution is clearly laid out in the table. Despite these benefits, managing the DP table introduces its own complexities, particularly in terms of initialization and bookkeeping.
After evaluating both optimized strategies, the chosen approach is recursive backtracking with memoization.
While both recursive and dynamic programming methods share similar time and space complexities, recursive backtracking is more intuitive for a problem involving string parsing and branching. Its recursive structure naturally handles the exploration of digit expansions without requiring the explicit initialization of a complex table. This simplicity makes it easier to implement and understand. Additionally, memoization ensures efficiency by avoiding redundant computations, allowing the approach to scale effectively for larger strings. There are trade-offs to consider. Recursive backtracking may encounter stack overflow issues for extremely large inputs, but this is mitigated by the efficiency of memoization. Dynamic programming, on the other hand, avoids recursion depth problems but requires careful management of the DP table, which can be cumbersome. In conclusion, recursive backtracking with memoization strikes the right balance between simplicity, efficiency, and scalability, making it the preferred strategy for this problem. To start, let's break down the encoded format of the input strings. Each of the two strings, S1 and S2, contains digits and letters. The digits indicate how many times the next block of characters should be repeated in the decoded string. For instance, the string 3A2B translates to AAB. The problem we need to solve is to determine if there is at least one decoded version of S1 and S2 that results in the exact same string. However, there are challenges to address. First, the two strings might have different compressed formats, meaning they could encode the same information in entirely different ways. Second, the repeat counts can create varying lengths and patterns when decompressed. To tackle this, we'll use a recursive backtracking approach. This approach simulates the decoding one step at a time, comparing the strings character by character as they are expanded. This method is efficient because it avoids fully decoding the strings, focusing only on the parts that matter for the comparison. Now, let's outline the step-by-step process of the algorithm. We start by parsing and expanding the strings. Two pointers, I and j, are used to track the current positions in S1 and S2. At each step, we parse the strings to extract the repeat count and the next character to be expanded. Once we have this information, we simulate the decoding process. Here, two counters, count 1 and count 2, are used to track how many repetitions are left for the current blocks of S1 and S2.
If both counters are greater than 0, we compare the current characters.
If the characters don't match, we return false immediately. If they do match, we decrement the counters to process the next repetition. When a counter reaches 0, we advance the corresponding pointer to the next block of the string and parse the new repeat count and character. It's also important to handle edge cases, such as when one string finishes decoding earlier than the other. In such cases, we return false. If both strings finish decoding at the same time, we return true to indicate they are equivalent. We continue by making recursive calls to repeat this process until we either fully decode both strings or identify a mismatch. The base cases are straightforward. If both pointers reach the end of their strings simultaneously, we return true, since the strings match. If only one pointer reaches the end, we return false, as they are not equivalent.
Let's also consider the complexity of this approach.
The time complexity is O, n plus m, where n and m are the lengths of S1 and S2. This is because parsing and comparing the blocks only requires linear time relative to the input size. The space complexity is O(1), as we do not store the fully decoded versions of the strings. Instead, we use a constant amount of extra space for variables like the pointers and counters. This makes our solution efficient in both time and space.
There are a few key insights that make this algorithm effective.
First, we avoid fully decoding the strings, which can be computationally expensive, particularly when the repeat counts are large. Instead, we simulate the decoding incrementally to save time. Second, the character-by-character comparison helps us catch mismatches early, reducing unnecessary computation. The recursive backtracking approach is another highlight, as it dynamically adapts to differences in the repeat counts or block sizes between the two strings. Lastly, we account for various edge cases. For example, strings with no digits, such as ABC versus ABC, are handled seamlessly. We also correctly handle mismatched lengths after decoding, like 3A versus 2A1B, and scenarios involving large repeat counts, such as 100A versus 100A. These insights ensure that the algorithm is robust and reliable. The algorithm relies on a few essential data structures to achieve its efficiency. First, we use two pointers, one for each string, to track the current positions during the parsing process. These pointers allow us to process the strings without fully decoding them. Next, we use counters, count 1 and count 2, to keep track of the remaining repetitions for the current blocks in S1 and S2. These counters are crucial for simulating the decoding without expanding the entire string. Finally, the recursive stack maintains the state of the comparison process at each level of recursion. This stack structure enables the backtracking mechanism to explore alternative paths when repeat counts or block sizes differ between the two strings. Together, these data structures form the backbone of our approach. At the heart of this algorithm are a few key operations. Parsing is the first step, where we extract the repeat count and character block from the current position in the string. This operation ensures we process the input incrementally, block by block. Next comes the comparison step, where we check if the current characters and their repetitions in S1 and S2 match. If they don't, we can terminate early. Recursive calls allow us to dynamically process the next blocks in the strings as needed, ensuring we adapt to varying block sizes and repeat counts. Lastly, edge case handling ensures the algorithm behaves correctly in scenarios like one string finishing earlier than the other or mismatched lengths after decoding. These operations work in harmony to provide a robust solution to the problem. Here, we begin the Python implementation by defining a class called solution and a method possibly equals within it. This method takes two parameters, S1 and S2, which are the encoded strings we need to compare.
To optimize our solution, we use the ru_cache decorator from the functools module, which memoizes the results of the recursive function DFS to avoid redundant computations.
The DFS function is designed to explore all possible ways the strings can match by considering their current indices I and j, as well as a diff value that tracks the difference in lengths between the interpreted portions of S1 and S2. First, we check if both strings have been completely processed, meaning I has reached the end of S1 and J has reached the end of S2. If so, the strings are considered a match only if diff is 0. Next, we handle the scenario where the current character in S1 is a digit. Using a loop, we construct the numeric value by iterating through consecutive digits and updating the number variable. If interpreting this number and moving forward in S1 results in a valid match, the function returns true. Similarly, we handle the case where the current character in S2 is a digit, constructing the numeric value and trying to match by adjusting the diff accordingly. If any recursive call results in a match, we return true immediately. Now, we address the case where both S1, I, and S2, J, are non-digit characters.
If diff is 0 and the characters match, we recursively check the next indices in both strings.
Alternatively, if diff is positive, it means the interpreted portion of S1 is longer, so we attempt to reduce diff by matching the next character of S1 with the current character of S2. Conversely, if diff is negative, meaning the interpreted portion of S2 is longer, we try to match the next character of S2 with the current character of S1 while increasing diff. If none of these conditions hold, or no valid match is found, we return false.
Finally, the DFS function is initiated with starting indices 0 for both strings and an initial diff of 0. This ensures that all possible interpretations are explored to determine whether the original strings can be equivalent. Here, we begin by defining the Java implementation for the problem. First, we import necessary libraries and create the solution class. The core function is possibly equals, which takes two encoded strings, S1 and S2, as input. It initializes a memoization map to store intermediate results and calls the helper function DFS. The DFS method is responsible for recursively checking if the strings can represent the same original string. It takes several parameters, the two strings, indices I and j for their current positions, a diff variable to track the difference between the lengths of expanded segments, and the memo map. Inside DFS, the first step is to generate a key for the current state using the indices and the diff. If this state has already been computed, we return the cached result from the memo map. Next, we handle the base case. If both strings are fully processed, the result depends on whether the diff is 0, as this indicates the segments align perfectly. Following that, we handle the situation where the current character in S1 is a digit. We iterate through possible numeric values starting from this position, updating diff by subtracting the number and recursively calling DFS for the next state. If this path leads to a valid match, we store the result in the memo map and return true. Continuing with the DFS implementation, we now handle cases where the current character in S2 is a digit. Similar to S1, we extract numeric values from S2 by iterating through consecutive digits, updating diff by adding the number, and recursively calling DFS for the next state. If this path leads to a valid solution, we record the result in the memo map and return true. Next, we address the scenario where both S1 and S2 have non-digit characters at their current positions. If the diff is 0, the characters must match for a valid alignment. We check this condition and proceed recursively if it holds. If the diff is greater than 0, it indicates that the segment from S1 is longer than the corresponding segment in S2. In this case, we attempt to skip the current character in S1, decrementing the diff and calling DFS again. Each of these checks ensures that we explore all possible alignments while adhering to the constraints dictated by the diff value. If a valid alignment is found through any of these paths, we update the memo map and return true. Finally, we handle the case where the diff is less than 0, meaning the segment from S2 is longer than the segment from S1. Here, we skip the current character in S2, increment the diff, and make a recursive call to DFS. If this path leads to a valid alignment, we mark the current state as true in the memo map and return true. If none of the cases lead to a valid solution, we store false in the memo map for the current state and return false. This ensures that redundant computations are avoided in future recursive calls. With this, the DFS method systematically explores all possibilities using backtracking and memoization, making the solution both efficient and exhaustive. The possibly equals method ties everything together by initiating the recursion and returning the final result. This approach ensures that we can handle both numeric compression and character alignment between the two encoded strings effectively. In the first example,
we are tasked with matching the strings s1 equals a2b and s2 equals 1ab. We begin with indices I equals 0 and j equals 0, and a diff of 0, which represents the current difference in decoded lengths between the two strings. At the initial step, s1 I is at int s2 j is 1. Since s2 j is a digit, we decode it to get the number 1. This means we consider adding 1 to the length difference, so we recursively move forward with the updated state, I equals 0, j equals 1, diff equals -1. Now, at the next step, s1 I is still a, and s2 j is also a. The characters match, and with diff equals -1, we adjust the difference by adding 1 to bring it back to 0. We then move forward to the next state, I equals 1, j equals 2, diff equals 0. At this stage, we have I equals 1, j equals 2, and diff equals 0. Now, s1 I is 2 and s2 j is b. Since s1 I is a digit, we decode it to get the number 2. This increases the length difference, so we update diff to 2 and move to the next state, I equals 2, j equals 2, diff equals 2. Here, s1 I is b and s2 j is also b. The characters match again, and with diff equals 2, we decrease the difference by 1 to diff equals 1. Finally, we proceed to the state, I equals 3, j equals 3, diff equals 0. At this point, both strings are exhausted, and diff equals 0. Since we've matched both strings successfully, we return true for this example. In the second example, we are given s1 equals 3 and s2 equals a2. Starting with I equals 0, j equals 0, and diff equals 0, we see that s1 I is 3 and s2 j is a. Since s1 I is a digit, we decode it to get 3, which increases the length difference to diff equals 3. We move forward with I equals 1, j equals 0, diff equals 3. Now, s1 I is at int s2 j is also a. The characters match, so we adjust diff by subtracting 1, resulting in diff equals 2. We proceed to I equals 2, j equals 1, diff equals 2. At this step, s1 is exhausted, but s2 j is 2, which is a digit. We decode 2 from s2, reducing the difference to diff equals 0. Finally, we move to the state, I equals 2, j equals 2, diff equals 0. At I equals 2, j equals 2, diff equals 0, both strings are exhausted, and the difference is 0, meaning the strings match. We return true for this example. Now, let's consider a third example with s1 equals a 10b and s2 equals a 1b. Starting at I equals 0, j equals 0, and diff equals 0, we see that s1 I is at int s2 j is also a. Since the characters match and the difference is 0, we move forward to I equals 1, j equals 1, diff equals 0. Here, s1 I is 1 and s2 j is also 1. From s1, we decode a number 10, which increases the difference to diff equals 10. We then move to I equals 3, j equals 1, diff equals 10. At I equals 3, j equals 1, diff equals 10, s1 I is b and s2 j is 1. Since s2 j is a digit, we decode it to get 1. This reduces the difference to diff equals 9, and we move to I equals 3, j equals 2, diff equals 9. At this point, s1 I is b and s2 j is also b. The characters match, but the difference remains diff equals 9, which cannot be adjusted to 0. As a result, we return false for this example. Summarizing the outputs, example 1 returns true, example 2 returns true, and example 3 returns false. To analyze the time complexity of the possibly equals function, we begin by understanding the state representation in our depth-first search with memoization. The function is defined by 3 parameters, I, the current index in string s1, j, the current index in string s2, and diff, which tracks the difference between the lengths of the decoded portions of s1 and s2. For I and j, there are at most len, s1, and len, s2, unique values, respectively. The diff parameter, on the other hand, can range from len, s2, to len, s1, depending on the lengths of the two strings. This gives us a total range of O, n plus m, possible values for diff, where n is the length of s1 and m is the length of s2. Multiplying these together, the total number of states we need to consider is O, n asterisk m asterisk, n plus m. Now, let's consider the work done within each state. In each recursive call, the function may need to process digits in the strings or directly compare characters. Processing digits involves parsing numbers, which can take up to O log x time, where x is the value of the number being parsed. Since the maximum number of digits in a string is proportional to the length of the string, this parsing time is bounded by O log n. Therefore, the work done per state is O log n in the worst case. Combining this with the total number of states, the overall time complexity of the function becomes O n asterisk m asterisk n plus m asterisk log n in the worst case. This reflects how the memoization and state exploration interact to determine the efficiency of the algorithm. For the space complexity, we start by examining the memoization table created by ru_cache. This table stores the results for all unique states, I, j, diff. As we determined earlier, the total number of such states is O n asterisk m asterisk n plus m. Since each state stores a Boolean value, the space required for memoization is proportional to this number of states. Additionally, the call stack depth is determined by the maximum recursive depth, which is proportional to the combined lengths of the two strings, or O n plus m. When we combine the memoization table and the call stack, the overall space complexity of the algorithm is O n asterisk m asterisk n plus m. This is an efficient use of space, considering the complexity of the problem. To put this into perspective, let's compare the optimized approach to a brute force method. In a naive brute force approach, we would generate all possible decoded strings for S1 and S2 and compare them. However, the number of possible decoded strings grows exponentially with the number of digits in the strings, leading to a time complexity of O, 2 to the power of n asterisk 2 to the power of m. This is clearly infeasible for large inputs. In contrast, our memoized depth-first search solution avoids redundant computations by caching results and pruning unnecessary branches. By limiting the exploration to valid states only, the exponential growth is reduced to polynomial time, as we've calculated earlier. This demonstrates the significant advantage of the optimized approach. Finally, let's break down the best, worst, and average case scenarios. In the best case, the strings contain no digits, and all characters match directly. This eliminates the need for number parsing and significantly reduces recursive branching, resulting in a complexity of O n asterisk m. The worst case occurs when both strings are filled with digits, leading to maximum branching and the need to explore all possible string lengths. In this scenario, the complexity is O n asterisk m asterisk n plus m asterisk log n. On average, the complexity lies between these two extremes, depending on the mix of digits and characters in the strings, as well as how effectively early pruning can minimize the search space. The polynomial time complexity we derived is justified mathematically by combining the size of the state space and the work per state, which ensures that each state is computed only once. This optimized approach is what makes the algorithm significantly more efficient than a naive solution. One common mistake in solving this problem is forgetting to handle nested encodings. For instance, when you have a pattern like 3, A2, B, it's important to decode the inner portion, A2, B, before applying the outer multiplier. Neglecting this sequence often leads to incomplete or incorrect results. Another frequent issue is not validating the input properly. Developers sometimes assume that inputs will always be well-formed, with non-negative counts, balanced brackets, or valid characters. This assumption can break your solution when faced with edge cases or invalid inputs, potentially causing runtime errors. Finally, using inefficient string construction methods is another pitfall. For example, concatenating strings in a loop with s plus equals can result in O n squared complexity due to repeated copying of the string in memory. Instead, it's much more efficient to use a list to append pieces and then join them at the end for O n performance. Another mistake to watch out for is mixing iterative and recursive logic. For example, using recursion to handle nested decoding while relying on iteration for outer decoding can create significant state management issues. This is especially problematic when working with stacks, as it becomes harder to maintain clarity on the state of counts or partially decoded strings. Misinterpreting digits or characters is another common issue. For example, assuming that all digits are single-digit numbers can cause incorrect repeat counts, especially for patterns like 10, A. This oversight can lead to inaccurate decoding. To avoid these issues, focus on recognizing patterns such as nested structures and leverage a stack-based approach, which is a highly effective way to parse and evaluate these kinds of expressions. It's also crucial to manage state carefully. Keep track of counts, the current string, and any previous context separately. Using a stack is often the most reliable way to maintain this information. Finally, don't forget to test edge cases rigorously. Inputs like 3, A2, B, C, 2, ABC, 3, C, D, E, F, or 10, A10, B, are excellent for evaluating the robustness of your solution. Remember, interviewers value solutions that are both correct and optimized, so avoid naive approaches like direct string concatenation. Instead, use efficient techniques like lists for building your result. This problem has strong connections to several related problems on LeetCode. For instance, LeetCode 394, Decode String, is the core problem for this topic and a great place to start if you want to deepen your understanding. LeetCode 726, Number of Atoms, involves similar stack-based parsing techniques, while LeetCode 150, Evaluate Reverse Polish Notation, and LeetCode 224, Basic Calculator, both require parsing and evaluating nested expressions, making them excellent companion problems. When it comes to solving this type of problem, there are alternative approaches to consider. A recursive approach, for example, works by breaking down the problem into smaller subproblems, decoding inner strings first. This method is often simpler to understand but comes with the trade-off of potential stack overflow for deeply nested inputs. On the other hand, an iterative stack-based approach uses a stack to track counts and partial strings as you parse through the input. This method is more robust for handling deeply nested structures but can be slightly harder to implement cleanly. Each of these approaches has its strengths and trade-offs, so the best choice often depends on the constraints of the specific problem. Another alternative is the two-pointer method, which tracks the current position and repeat counts without explicitly using a stack. This technique involves using 2 pointers to parse the string while keeping track of the repeat counts directly. The main advantage of this method is that it avoids the extra memory usage required by a stack, making it more space efficient. However, it's less intuitive when dealing with deeply nested strings, as managing the state of the decoding process without a stack can become complex. Ultimately, this approach is best suited for scenarios where memory optimization is a priority, and the nesting depth is relatively shallow. By understanding these variations and their trade-offs, you can choose the most appropriate strategy based on the problem requirements and constraints. Thank you for joining me on this problem-solving journey. We explored how to decode and compare 2 encoded strings, gaining insights into recursive backtracking and string manipulation. I hope you found this session both informative and engaging. Don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!